All right, so welcome back. Welcome back to this YouTube channel. So in the last video, we have learned about, we have developed a deep convolutional GAN in TensorFlow using TensorFlow. So it was a relatively easy tutorial. You might have thought, there is a lot of things behind these image generation models, but in fact, it is pretty simple if you are if you like experimented with the architecture and all that. In this video, we are going to just upgrade our knowledge just a little bit by learning about conditional GANs. Conditional GANs. So remember that we are using generative adversarial networks here, and there are many more um, types of GANs or generative models. Like for example, if you look at things like mid journey, stable diffusion, and all that, so they are not actually using GANs, but they are using stable diffusion and variational autoencoders, and there are some models which use GANs also. So I just want to remind you that there are many more models, and I think you have come to the right place. This is the right this is the right time for you to start learning about GANs, because if you learn about GANs, you will be comfortable with learning other things too. I'll cover everything here in this channel. So I actually came across this really good tutorial by Jeremy Howard. You know, he has a company called Fast AI. He teaches deep learning. So he has this very lengthy tutorials, very lengthy, 27 videos, each 2 hours, just for stable diffusion. He just taught only stable diffusion for almost 27 videos, and each with a length of almost 2 hours, on average 2 hours. So just like, it's a very good tutorial. It's actually part two of practical deep learning, so a little advanced level. I'll also be covering that. I'll try to cover this also in a relatively shorter time, because there he's a researcher, and I think they have put a lot of material together, especially the latest material. I'll try to cover these things faster in the upcoming video, so just stick around with me. So in this video, we're going to we're just going to upgrade our knowledge. So just give me a minute. I'll just plug my whiteboard. So yeah. Okay, so hope you can hear me. Yeah. So I'll just plug my whiteboard. So yeah, in this video, we are going to just upgrade our knowledge, as I just said. We are going to learn how we can control, how we can control what our generative or what our GAN should produce. So we will learn to control the output of our GAN. Essentially, in this over the past few videos, when you learn about generative adversarial networks, you have seen that the GAN will just generate um the just random image based on the training distribution. Based on the training data, it'll just generate a random image. But how can we actually control what it produces? For example, in the case of MNIST data, right? In the case of MNIST data, um, how can we control what number? For example, what number it has to predict? For example, how can we say that predict 0 and it will predict a 0? So how can we or create a 0, create an image of the digit 0? How can we do that? So the idea is actually pretty simple. We don't do anything very fancy or crazy, but the idea of conditional GANs is actually controlling what to predict. Let's say, for example, you have multiple classes, and you train the generative model on all of these classes, and you can just control what class of data it has to you know uh, predict, right? So I don't think I'll need. So we'll be doing that in this video, and then just stick with me. We'll do it together. Now it will be working. So I have this code. Um, this little notebook. It'll take so much while to train. Let me tell you, like one epoch just took me around 1 hour. And if you want to have a better model, you have to at least train for like 100 epochs, which will of course take like 40 hours to train. I'm using the collab free GPU. So that is a like huge amount of training. You have to do a true huge amount of training. But no problem. Now we'll just go through the code. You have, if you have like if you are rich and have access to powerful GPUs, then go try. If not, then you know just keep on using these pre-trained models, right? For people like us. So I'll go through the code step by step. So just right. So first, in this first cell, we'll import the necessary libraries, the libraries that we'll be using. First, we'll import the expand dimension library, NumPy. We'll import the zeros and ones library to generate random zeros. We'll also input the random function or random function from NumPy to actually predict, to actually generate the random noise, right? So the generator model actually takes in this random noise as the input. So therefore, we'll also be using random library to actually generate random noise, right? So we'll be using that. And then we'll also be loading the MNIST data, the digits data, all the handwritten digits data. We'll be loading that. We'll be importing that data from tf.keras.dataset.mlist. And then we're also going to import Adam optimizer. For optimization, we'll import model to actually create a model function pipeline. We'll import a bunch of layers: dense, reshape, flatten, convolutional 2D, con 2D transpose, leak value, dropout, embedding, concatenate. So I hope you are all aware of these functions, because if you are not, I would definitely recommend you to check my previous videos and then come back, because I have teased them. And yeah, even if you have basic idea of TensorFlow, then this video is for you. So first, yeah, we have imported the libraries that we'll be using. These are all the libraries that we'll be using for building our project. And then I'll create a function called define discriminator to actually create the discriminator first. So the input shape is of course 28 by 28 by 1, because our images are in the shape of 28 by 28 by 1, right? 28 28. Uh, just not an RGB image, just a black and white image. So therefore, we'll have 28 by 28, and the number of class is 10. The number of classes, output class, that is, we'll have 10 digits: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So as we are going to have 9 digits, we are going to set the number of classes equal 10. So I'm going to create the model here. First, I'll have, so we are going to have two inputs, right? So we're going to have two inputs. That is why you see here I inputted two inputs: input image and the input label. So we are also we are while building the discriminator, we are not only going to take the GANS output, right? So we are not only going to take the GANS output, we are not only going to take the GANS output and predict how good that output is, but we are also going to take the label that that the GAN has to predict, or the generator has to predict. GAN is not a very good terminology there, but we'll not only take the image generated by the generator, but also the label that it wants to generate, that the user wanted it to generate. And then based on that, we'll generate the prediction, like how real is that, right? First, we'll take the input label, the label, whatever number that is, that the GAN wanted to predict. And then we'll have this, and then we'll create an embedding taking this input label. So we'll just take this input label. Like you could create embeddings, even like the label does not have to be words to create embedding. You can just create this feature representation for this in label, such that this in label is better understood by this model. So we'll just create an embedding, which will of course be updated while in the time of optimization. And then we'll create the number of nodes. Number of nodes is nothing but input shape into input shape. So we'll get the number of images into number of like 28. So that is the number of nodes here. I'm going to pass this label right? I'm going to pass this label. So I'm going to pass this embedding representation, or I'm going to pass this input representation of this input label. For example, I want to predict the digit called 0, right? The generator wanted to predict the digit 0, and it generated an image. So we are going to take this input label, the generated image, and pass that to a dense layer, and then we're going to reshape that output. And then after reshaping it, we have finished one tree, right? I think I'll just open whiteboard here. Just bear with me for 1 minute. I think I've wasted a lot of your time here. I'll try to provide you more value in less time from now on, or from next on. I think I'll just draw with my mouse here. I've wasted enough of your time. So yeah, so we are actually essentially creating two trees here. So the discriminator, this is the discriminator. It takes in one output, one input. It is going to take the label. I'm going to say LA, and then it is going to take uh the noise. I'm going to say NO. Oh, sorry, not the noise. This is not the generator, right? This is the discriminator. It's going to take the label and the image. So it is going to, what we have done here is we are going to pass this label to an embedding, and then we are going to pass that embedding to a dense layer, and then we'll reshape this layer. And then after we have reshaped it, we'll take another input. We'll take the input image. We'll just take this input image, right? We'll just take the input image, and then we're just going to concatenate this input image and this um this representation or this output. This output is nothing but the output of the previous dense layer. So the output of this previous dense layer and this image will be concatenated. We'll just add this up because they are of same shapes. That is why we have done a reshape here. As you can see here, if you see here, it is this shape is nothing but the shape of this image, right? So after performing the dense layer on this embedding of the input label, we are just going to reshape this into the exact shape of this image that we are going to get. And after we get this image, we are going to just concatenate them. And after that, we are just going to have some classic convolution layer. We're just going to have a convolution layer, and after that, we'll perform ReLU, and then con 2D, and then again con 2D, ReLU, flatten, and drop out, and the final dense layer. So remember this is this is discriminator, so therefore we will be not having convolutional transpose. We are just going to take that image and the label and just going to predict how real that image is generated by the generator, right? So the generator is the discriminator is, we have defined the discriminator, and remember we are using atom optimizer and the learning rate is pretty small, and then we are also setting the beta parameter just to, I think, add or multiply after optimizing, right? And then we are going to compile the model with the loss of binary cross entropy, because of course we are going to predict if the image is real or not. And then we're going to have the matrix is accuracy, and we're going to use atom optimizer, and this function returns this model object of the actual model. We can just train it because it's already compiled. And I'll create the generator class, right? So let's build the generator now. So we'll be here also in the generator also we'll be taking the input label and the noise vector. In the previous discriminator, we have taken the input label and the image. Here we'll be taking the input label, and the noise vector, which is completely random, of course. So I'm going to create this class, and the input, as you can see here, is latent dimension, the dimension of this noise vector, and then the number of classes here, of course, 10. And then I'm going to take the input label. I'm going to create an input layer which takes in the input label with a shape of 1 comma. That is, we are going to have a one number because it is a say like category. So I'm going to create an embedding of, again I'm going to here also create a feature representation of this class or label. I'm going to create the number of nodes. I'm going to again pass this embedding through a dense layer. I'm going to pass this label to through a dense layer. So essentially, after going through this dense layer, this input is going to be, this input label will have a higher higher order of representation, or higher what is that, higher dimensional representation. And after that, I'll reshape it into 7 by 7 by 1, right? And then I'll also take this input noise. I'm going to take the input as the input noise. And then after taking the noise as the input, I'm going to again pass this noise. I'm going to pass this noise to a dense layer, through a dense layer of this shape, 128 by 7 by 7. And then we'll perform ReLU, reshape, and then we'll concatenate. After, so here in the generator, we'll be taking this LA label, and then N, and we are going to perform dense reshape. Here also we're going to perform dense reshape. And after performing that, after performing this, we'll concatenate. We'll just add them both. Right? So that is what you see here. After we have this gen, which is nothing but taking this noise vector, we'll perform dense layers. And after we get the output to be in the specific required shape, we'll just add these both gen and the input level embeddings. So then the dense output of this input level embeddings. Then after we have merged them, we can actually pass them into convolutional 2D transpose, as we have looked at in the last videos. One of the last video, actually in the last video, no, before that video, sorry. I don't actually remember. I have very poor memory power. So anyway, so we'll be passing that through a convolutional 2D transpose. The operation that I've showed you in one of the last videos. And then I'm going to have 128 filters of 4 by 4 each. The shape of each is 4 by 4, and then the stride is 2 by 2. I'm going to pass 2 at a time. And then we are going to have padding also. We are also going to add padding. And then leaky ReLU again. And then again, we'll do convolutional 2D transpose, leaky ReLU again. Again, the final convolutional 2D layer, whose output is, whose output will be the image, right? So this, the output of this model should be the image, right? So this will be the image. And then we could actually right, so we can, after we have built the generator and the discriminator, we could actually define our GAN. So the input of this function, we actually create a new function, define GAN. We can just combine all of the generator and the discriminator. This function takes in the input as G model and D model. So here G model represents the generator, and D model represents the discriminator. I'm going to first set the D model to be not trainable. So I'm first not going to be training the D model, the discriminator. So first what I'll be doing is, I'll first train GAN and then the discriminator. So just see how it goes. First I'm going to get this GAN's input, G model's input. I'm going to get this G model's output, right? And then we'll just be I'm going to, after I get the output of this GAN, I'm going to pass that through D model, and then we can just concatenate all of them. I'm going to create a model object which takes in the input as GAN noise and GAN label, so gen label and gen noise, and then the output is going to be this GAN output, right? So which is going to be the output of this GAN, right? So and then after that, I'm going to use the Adam optimizer, and then I'm going to compile this model with using binary cross entropy, the discriminator essentially, and I'm going to return this model. So that is the idea. I'm going to run this. Right, there's no need of running because I'm not going to train it before you, just because of the simple fact that, like, if you look at this architecture, it is pretty sophisticated, it's pretty large. So therefore we are not going to train this model. It might take, I don't know, 40-50 hours if you want to train it, like, to be really good. And then I'm going to create, anyway, we'll move on. I'm going to create this function to actually pre-process data, to actually get this data, right? Sorry for that. I'm going to create this function called load real samples to actually get the real data, right? Whenever you are training GAN, you will get the real data, and based on the real data, the discriminator has to differentiate between this real data and the generated data, and based on the discriminator performance, the generator will update its weights. So that is the idea, right? We're going to do that. So we're going to get this real data from this MNIST data set. right? So I'm going to call this function called load data. I'm going to we have imported that in this above section. I'm going to expand the dimension. I'm going to convert them into floats. I'm going to do some pre-processing, and then we'll finally output this x and the train y. Train y is nothing but the labels, and train x is nothing but, or x is nothing but the images. X is images and y is the labels. And then we're also, I'm going to create another function, which is, I'm going to take the data set. I'm going to extract the images and labels. And then here also we are outputting images and labels, right? Just leave it. Now let's here we are generating these latent points, just this noise vector. Here we are using this random function of numpy to actually create random, like random random noise. And then we'll create another function called generate fake samples. We'll just call this generator, right? So we'll call the generator, and then to actually, so we'll just, this function actually takes in the generator and the latent dimension and number of samples, and based on that it'll just generate a new image based on this label and uh, based on the label and the noise, latent noise, right? So I'm going to call this function that we have previously built here. I'm going to call this function to actually create this noise, right? And then we are going to do that for every sample in the generator. We are going to generate an image for every sample, and then we'll pass all of this image that we have generated for every sample to the discriminator, and we'll calculate the loss based on the discriminator performance, update our generator and update our discriminator. And hopefully we will actually be able to create a war between generator and the discriminator, and hopefully both will try to compete together, and hopefully, I used the word hopefully a lot here. Yeah, they'll both converge, right? So they'll both perform better. All right, so I'm going to, yeah, there's no need of running. So I have created the final train function to actually train our model. Okay, so this function, I'm going to call that as train. The inputs are G model, D model, the GAN model, the data set, the latent dimension, the number of epochs, and the batch size or number of batches. Well, I'm going to calculate the batch per epochs, which is nothing but the number of images by the number of batches, right? The batch size, like the number of images per each batch. And then I'm going to cut the half of this batch, right? And then we'll finally build the training loop here. I'm going to go through, I'm going to create a for loop that goes through the number of epochs. So that is going to run. So all this code in this body will going to run for number of epochs here 10 times. And then in each epoch, we are going to go through each batch. So we're going to keep on updating these weights for each batches, which of course, because batch training, batch gradient descent is always better, right? And then after that, we'll first generate an image, right? And then we'll generate the fake samples. We'll generate the real samples, and then we'll generate the fake samples, right? And then we'll train both our discriminator, right? We'll train our discriminator, and after we train our discriminator, right, we'll generate latent points to input for our generator, and then we will be calculating generator loss, G loss, right? Here we are generating the fake samples here, and then we'll be calculating the G loss here, and then we'll be updating them, right? We'll be updating them. Yeah, this function, I think, yeah, this function is going to train our model. So as you can see here, we are running that on discriminator and the generator, hence updating our parameters, right? We're going to run this. We're going to like add up all of these functions that we have previously built into this one big function, in which we'll first call the generator. First we'll train the discriminator on both the real and the fake, and then we'll train the generator by generating the images from the from the noise, and then the generator will be forced to predict on these fake samples. And then if it predicts good, the generator loss is going to be lower. If it does not predict, if it predicts, if the discriminator is fooled right? The generator will have lower loss. If the discriminator is not full, the generator will have a relatively higher loss. So after that, we can just use this thing. This block will first create the discriminator, the generator, right? We'll just create an objects of this function, or we'll just call this function into this variable d model and g model, and then we'll finally assemble our GAN from both the generator and the discriminator using this function that we have previously built, define GAN, and then we can load the real samples. Sorry, we can load the real samples and finally call this function train given this input. So as you can see here, it's a very long process, believe me. Like if you even don't even try to experiment to run this on your computer, on your local machine, without using Colab, because if you try to run it on your local machine, I'm telling you, if you are not anyone richer, if you don't have NVIDIA RTX 4090, then your computer is going to I don't know, like get heat up very fastly. So yeah, that is it for this video. So hope you have learned something. In the next video, we are going to continue, maybe cover up some new types of GANs, right? So thank you for watching, and I'll see you in the next video.